So here's a further example about user-defined functions. This one, the function that's involved is somewhat longer. It certainly looks more complicated than we had before, but it's not that much worse. The idea here is to have a simple implementation of Euclid's algorithm for calculating the GCD of two polynomials. And it assumes that the inputs are univariate polynomials over a field. Now already this sentence here should actually be ringing alarm bells for you. It's any function that you write that you're going to give to someone else should never assume anything about the inputs. It should always check the inputs. So as I said before, we'll skip this for the time being because that's not what I want to highlight here. Although we will see later on part of the dangers of making these assumptions rather than checking explicitly. Now, before we get to the interesting function, the one does the real work, I want to introduce an auxiliary function. So again, this danger word assume. We're assuming that f is a univariate polynomial. And we want to return the indeterminate in f. So I call this function getIndet for the moment. And it has one argument, which is a polynomial f. Once again, as I say, for simplicity, we're not checking that, but we should in a proper version. So first thing we do is we get the ring of our polynomial, so we know that's going to be a polynomial ring. Now we're then going to try for each, so here's a different loop. So previously we had a for loop where we could iterate over integer values. Now here we have a for each loop with the keyword for each and ending with the keyword end for each. So for each, and then we have the loop variable here, which I've chosen to call x. So for each x in, and then whatever expression I have here has to be a list. So it'll then iterate over the elements of the list one at a time, starting at the first element, then the second, and so on until it gets to the last one. So for each x in the indets of P, it then executes the body. In this case, the body is just a single line long. All we're checking is if the leading power product of our polynomial is divisible by x, then we return x. End if. That's all we have to do here. Oh yes, so this is something that's easy to forget. If we have an if, oops, wrong arrow here. If here we have if followed by a condition followed by the keyword then one or more commands what to do if the condition is true. Not sure whether we've seen an else yet. There's an optional else here, and then we must end it with an end if. If we miss that out, CoCoA will complain. It's something that's quite easy to do. Many other languages don't require an end if, so I've been caught out many times here. So in the same way that we have for each ends with end for each, if ends with end if. And then assuming that f really is a univariate polynomial, we'll never get here, supposedly. There's in fact a bug there. That statement's not correct, but it's correct enough for this example. So that's our auxiliary function. So given a polynomial, it returns an indeterminate, or the indeterminate that polynomial is in, assuming that the polynomial is univariate. And then we're going to use that inside Euclid here. So Euclid, the function Euclid, takes two polynomials, both in the same, two univariate polynomials in the same variable, and it's going to calculate their GCD. Following the hint I gave before, I'd like to get rid of some trivial cases first. So if either of the polynomials is 0, we then return the other one as a GCD. If either of the polynomials has degree 0, in other words, so we now know at this point that neither of the polynomials is 0. Now if either of the polynomials has degree 0, that means it's a non-zero constant, then we simply return that polynomial as a GCD. So that's got rid of 4 trivial cases. Now the line I'm on here, we now want to check the degrees of the two polynomials. So we now know that neither polynomial is 0, nor is either polynomial constant. So both polynomials have degree at least 1. And now we simply, with this statement here, we check to see if f has lower degree than g, then we swap them over. So swap is a function that CoCoA supplies. Notice we got the ref here for the arguments. This is because both arguments, f and g here, are going to be passed by reference. That allows the function to change the value of the variables that are passed in. So f and g. So in particular, swap is simply going to swap over the values. So we would expect swap to be able to change the values of f and g. So we have to put ref in here. If we want to allow, and this applies to any function, you want to allow a function to change the value of one of its parameters, then it has to be passed in using ref. So that's something new we haven't seen before. So after if we get down to the line where my cursor is now, it's just a comment at that point, but if execution reaches here, we now know that the degree of f is greater than or equal to the degree of g, which is greater than or equal to 1. So we now enter the general loop for Euclid's algorithm. As far as I can see, this statement here, p equals ring of f, is not needed here at all. Initially I had the getIndet function I initially wrote in here explicitly. So I think I'll get rid of it. So we now get x is the indeterminate that appears in f. And here we have a double, so we have nested loops. So these are while loops. So we've seen for loops and for each loops. We now have a while loop here. So it's while, some condition, the keyword do, and then the corresponding end while at the other end. So this one's a little bit complicated because we have two while loops. We have an outer while loop and an inner while loop. And I've used indentation to try to make it easier to follow which instructions are inside the body of the outer loop and which instructions are inside the body of the inner loop. In fact, if I write the code in Emacs, then the indentation is automatic. So while g is non-zero, it then does the inner loop, which now does while f is non-zero and the degree of f is bigger than the degree of g. And you might wonder why I bother to check that f is non-zero. Oh yes, so please note here, so this less than greater than is CoCoA's way of saying not equal to. It's a bit unusual. Other languages use different symbols to represent not equal to. The one in CoCoA is less than greater than. So we need to do this test because the degree function, if I give it a zero polynomial, will give an error. It says the degree of the zero polynomial is not defined. So with CoCoA we have to be a bit careful here. So we have to check it. Excuse me. Have to check that the polynomial is non-zero and its degree is bigger than the degree of g. If so, we then do these two instructions here. One is the difference of degrees, so it calculates delta, the difference of the degrees, and the second one simply subtracts from f a suitable multiple of g to cancel the leading term. This is the standard implementation of Euclid's algorithm. So we keep going around this inner loop until either f is 0 or its degree is less than that of g. So we don't know, either of these conditions will cause it to stop. We call swap again, so we now swap the roles of f and g, and then we repeat the outer loop. So I'm hoping you're all reasonably familiar with Euclid's algorithm for univariate polynomials. If not, you can also find that, I'm quite sure, on Wikipedia or in many other sources. So once the outer loop's finished, so once g, so the outer loop ends when the polynomial g is 0. At that point, whatever we have in f is going to be the GCD. And so we return it and the function ends there. So let's give these to CoCoA. We have to read in both definitions. So I'll tell Emacs to mark these two and then send this to CoCoA. So there's the source region command up here saying that it CoCoA has read it. Excuse me. CoCoA has read it. Now we've read in the definition, CoCoA gave no errors, so that's good. So now we can actually try using the code. We can try testing it, see if it works. So let's just try an very easy case to begin with. We don't need to test anything too complicated. So we need to tell it what ring to use. So we use Q of x. So that's going to be univariate polynomials in x with rational coefficients. And we ask it to calculate the GCD of x plus 1 and x squared minus 1. And we choose an easy case like this because we also know what the answer should be. So let's see if it gives the right answer. Yes, so we knew already in advance that the answer should be x plus 1, and the code gave us x plus 1. Plus, we know from the way the code was structured, this was not one of the trivial cases at the start, but it actually went through the general case, the main loop. So we have some reason to hope that the implementation is essentially correct. So at least it worked on an easy one. We should be more cautious. We should try some slightly bigger ones. But let's jump ahead and we'll try one that's considerably bigger, and moreover we'll give it essentially random inputs. So I'm going to calculate here 3 random polynomials. So I calculate these as a sum of a random number multiplied by a power of x, where the exponent goes from 0 to 6 in each case. Not sure why I chose 6, but anyway. So I'm going to generate, so even these 3 lines here, the right-hand sides are identical. Since they're using the random function, we're not going to expect that f, g, and h will be the same. They're almost certainly going to be different. So we get CoCoA to evaluate these 3 polynomials. That didn't take long. Now it's going to get it to print out what it's about to calculate the GCD of. So I'll just do these 3 in a block. So it's going to calculate the GCD of these 2 polynomials. So f times g is this polynomial here, and g times h is another one. So we can see immediately that certainly f and h are different. So let's get CoCoA to calculate the answer. So it doesn't take too long, even though those polynomials are not that tiny. I calculated the GCD using Euclid's algorithm. And now let's check to see if it's correct. So we expect with very high probability that the GCD will in fact be equal to g. The only case it might not be is if for some remote chance f and h happen to have a common factor. That's extremely unlikely. So let's do that. Do we get the answer we expect? No, we don't. So what went wrong here? Why do we get false? Well, one possibility, as I said, is that f and h had a common factor that I didn't allow for. Well, that's extremely unlikely. So the answer we expected was g, which looks like this. The answer we actually got looks very different. So what's going on here? Well, it turns out that, of course, the GCD is in fact defined only up to a scalar multiple by a coefficient. And so we've got a fairly horrible scalar multiple here. If I divide the actual answer I got by the answer I expected, then I get a scalar number there. If you look carefully, you will see where the cursor is that this is in fact a rational number. So the first part's the numerator, the second part's the denominator. So that's a known disadvantage of Euclid's algorithm. That's why many years ago people worked hard to try to find a better way of calculating GCDs. So one disadvantage is it produces these nasty scalar factors, which we don't particularly want. And these have a consequence for the computer. It means the computer is, we can see up here, was computing with these rather nasty looking rational numbers rather than being able to operate with nice simple integers like we have here. And while the computer is very quick, it still takes the computer more time to work with these big rational numbers than it does with two-digit integers. So the bit I've highlighted here, we're going to do next, we give it a bigger example. So I'm just going to try with two polynomials, each of degree 99, and with coefficients in the range minus 999 to plus 999. And I want to try to calculate the GCD of these two. Almost certainly the GCD is, we would expect it to be 1. So let's try doing that. We'll see how long the computer takes. So it's running that Euclid function we saw before. And there it took about 7 seconds. Whereas if we do the built-in GCD function, so CoCoA already has a built-in GCD function, that was quick. That took 0.005 seconds, so at least 1,000 times faster. Did we get the same answer? Well, we could check. Answer 2, I would expect to be 1. Now the answer I got, we have exactly the same problem we had before, that the answer was almost certainly going to be correct. It would be 1 multiplied by some scalar factor. Let's have a look, see what we actually got. That was not very nice. So I suppose, yes, it's a bit tricky to work out how big that was. I can, if I ask Emacs, it'll tell me that my cursor here is in position 67,000 along the line it's on. So this is most likely a rational number with about 33,000 digits in the numerator and 33,000 digits in the denominator. It's not good that the computer has to work with such big numbers. So I guess in some sense I've worked out, well, I've given a hint as to why GCD is faster than what we're doing. In fact, it uses quite a few clever things which we don't have time to go into here. It uses something called a modular method, which avoids essentially these problems of sort of coefficient growth, sometimes quite drastic coefficient growth, even though the answer is strictly speaking simple. We can actually take the version of Euclid we had before and do some quite clever things to keep the coefficients smaller. I won't go into details, I can leave that as an exercise. And I'll give you as a hint to look up the CoCoA functions monic, for example, clear denom, content, and maybe prim. So that's almost all I wanted to say. So here's a bad example. So we're reasonably happy our code is working, at least up to a not very nice scalar factor. So let's try it on something more complicated. Let's try it on these two polynomials. So in fact, in this case, we give as input two univariate polynomials. One's a univariate polynomial in x, the other one's a univariate polynomial in y, and it's not going to work. Let's try. So computer's taking an extraordinarily long time for two such simple polynomials. What are we going to do? We fear that the computer may be stuck in an infinite loop or something. So we can go, so we need to do this slightly carefully. So we click so that the cursor is in the window where CoCoA is running. Then we can go up to Signals at the top, and we can press Break. We'll also notice that Break corresponds to pressing Control-C, Control-C. So Control-C twice. We select Break, and that stops CoCoA. So in fact, it was in an infinite loop. So how could we avoid this problem? Well, one of the answers there is we should check the inputs. So remember, we were making assumptions, so we should actually check the inputs properly. Otherwise, if we don't do that, then bad things can happen, like the computer gets stuck in an infinite loop. And then there's a CoCoA function called univariate indet index, which I looked at just the other day. it works, but it could be done better. And so if you're feeling keen, you could have a look at the function univariate indet index and see if you can find a better way of doing it. I'm not going to tell you how to find the definition of this function, but I'll give you just hints. Look up the keyword starting and the keyword describe. Okay, that's all I wanted to say.